With Coulomb's law, we can find the electric field created by a single point charge as kq over r squared. Now, we could do something similar with a moving charge creating magnetic field. This is the result of some special relativity calculations, which we're probably not going to get into. But the result of a moving charge is given by this formula right here. Now, as your textbook points out, there is no way for this magnetic field to be constant. If the particle is moving, then r changes, either in magnitude or at the very least in direction. If the particle is moving in a circle, r would change in direction, which would change r hat. And having a time-dependent magnetic field produces problems of its own, which we're not going to get into. So the next simplest solution is, instead of a single charge moving along a path, we have a bunch of charges moving along a path such that at any one point there are just as many charges going into it as coming out of it. I am, of course, describing current. So we can replace the Q times V with I times dl to talk about the charges moving in a current. And because we're talking about dl, because we're talking about a very small piece of the wire that this current is following, we're also talking about a very small piece of the magnetic field that is ultimately produced. The net result is what we call the Biot Savart Law. dB, the small piece of magnetic field, is equal to mu sub naught over 4 pi times, and this is where different textbooks will follow different conventions. Your textbook uses the convention I cross r hat dl. A lot of textbooks like to say, no, it is the L that's the vector, and writing it like this is wrong. It doesn't actually matter. Because when you're getting down to the level of formalism where that does matter, you're not going to be using I, you're going to be using current density with some delta functions. So this works well enough, I cross r hat over r squared, or and this is sometimes easier, I cross r vector over r cubed, because the r hat vector can be the r vector divided by r. Now I have used this symbol right here, mu sub naught. That is known as the permeability of free space. And this is kind of analogous to the permittivity of free space that we used when we were talking about electric field. The permeability of free space is given as 4 pi times 10 to the negative 7th Tesla meters per ampere. Note, this is not an approximation. The way that current is defined, mu naught is exactly 4 pi times 10 to the negative 7th Tesla meters per ampere. Now, to use the Biot Savart law, you need to take this dB and you need to integrate it. And the way you integrate it is going to depend on the situation. So let's look at the case of an infinite line of current. So we can use this image right here. And we can write, and now we have Q, V, or I, R, dl, and r squared, that we need to write them all in terms of S. So first of all, S being defined the way that it is, we can say that that the magnitude of this R vector is Pythagorean theorem, the square root of big R squared plus S squared. We can also say that the R vector is a vector going from the point on our wire to the point we are interested in. And that is big R in the I direction minus the value of S in the J direction. Next, we can say that this current is we're going to say it's going upward, which means it's going in the positive J direction. So I is IJ hat. And finally, the dl. dl is the differential piece of length. In this coordinate, each time you jump S by a little bit, you change the L by a little bit, so dl is equal to ds. So plugging all of these terms into our Biot Savart Law, well, this form of the Biot Savart Law, gives dB is equal to mu naught over 4 pi times ij hat cross r I hat minus sj hat over the square root of r squared plus s squared cubed, or sometimes you see it written r squared plus s squared to the 3 halves, then all times ds. Now, before I integrate, I want to point out this is ij hat cross ri hat minus sj hat. We can distribute the cross product, and j hat cross j hat is 0. So this portion of it, the minus sj hat, that goes to 0. And so all we're left with up here is ij hat cross ri hat. Now I and big R are constants, so I can pull them out. And j cross I is negative k. So pull out the constant mu naught over 4 pi, pull out this constant I and R, and we're left with just the negative k I had up here. Now, unfortunately, because r squared is added to s squared and then raised to some power, we can't pull this r out. So we're left with r squared plus s squared at the bottom. Now, one more thing, the bounds of our integration. We have an infinite line of current. It goes from negative infinity down here to positive infinity up here. And so you're left with that. Now, doing that integral can be kind of a pain. I would recommend looking at example 5.5. It walks through the math on a couple ways of doing this integral. I'm just going to go ahead and say this integral right here is 2 over r squared, which means that the total magnetic field at that point is given B is equal to mu sub naught I over 2 pi r, a result which you should remember from physics 2.